Hi, I am Arib. You are watching my YouTube channel. A wind energy power plant. Definition: a wind energy power plant is a wind energy system that turns the wind's kinetic energy into electrical energy. A wind power plant comprises a wind engine, an electrical current generator, automatic systems for controlling the wind engine and generator's operation, and structures for their maintenance and installation. How a wind turbine works. A wind turbine turns wind energy into electricity using the aerodynamic force from the rotor blades, which work like an airplane wing or helicopter rotor blade. When wind flows across the blade, the air pressure on one side of the blade decreases. The difference in air pressure across the two sides of the blade creates both lift and drag. The force of the lift is stronger than the drag, and this causes the rotor to spin. The rotor connects to the generator, either directly, if it's a direct drive turbine, or through a shaft and a series of gears, a gearbox, that speed up the rotation and allow for a physically smaller generator. This translation of aerodynamic force to rotation of a generator creates electricity. How a wind plant works. Wind power plants produce electricity by having an array of wind turbines in the same location. The placement of a wind power plant is impacted by factors such as wind conditions, the surrounding terrain, access to electric transmission, and other siting considerations. In a utility-scale wind plant, each turbine generates electricity, which runs to a substation where it then transfers to the grid where it powers our communities. Types of wind power plants. Wind energy power plants can be segregated into 4 types, which are as follow. Hybrid wind energy power plants. We can't rely on wind alone to generate power because it isn't completely reliable. Combining a wind energy power plant with another renewable energy source, such as solar energy, would be the ideal option. This type of layout is known as a hybrid arrangement, and it is beneficial in areas with a lot of sun and wind. Remote wind energy power plants. Wind turbines that are low maintenance for extended periods are required in remote areas with high wind speeds and frequency. This means that, even though they are considerably smaller than their standard equivalents, they should be able to withstand all weather conditions. Remote wind energy turbines are the name for these types of turbines, and they are constructed explicitly with these goals in mind. Horizontal axis. In a horizontal axis turbine, the orientation of the axis is kept along the horizontal axis. In a propeller-type turbine, a number of blades are 3 or less than 3. And in a multi-blade turbine, a greater number of blades are used. The propeller-type turbine is mostly used turbine. The propeller-type wind turbines are mounted on top of the tower, and the blade of this turbine is made up of an airfoil or aerofoil section. Two-blade turbines are the most cost-effective turbine. But in this condition, a yaw control system is required to mitigate vibration. This configuration is used for large units, 2 megawatts to 3 megawatts, with suitable material and control systems. A 3-blade design is the most used and preferable design, because the rotor is naturally balanced with a 3-blade design. This configuration is used for a wide range of power generation, 15 kilowatts, 3 megawatts. Multi-blade turbines are used 12 to 20 blades made up of glass fiber reinforced plastic. The diameter of the multi-blade rotor varies from 2 meters to 5 meters. The multi-blade turbine consists of curved sheet metal blades with inner and outer ends fixed with rims. Vertical axis. In this type of wind turbine, the main rotor shaft is placed to transverse the wind, and other accessories are placed at the base of the turbine. In Savonius type wind turbine, A hollow elliptical cylinder is placed into two pieces, and each piece makes half of the vertical turbine fixed to a vertical axis. The shape of this rotor looks like the alphabet S. Therefore, Savonius-type rotor is also known as the S-type rotor. In Darius-type wind turbine, it consists of 2 or 3 blades. These blades are curved in shape, and the shape of this blade is known as troposkene. The blades with aerofoil or airfoil cross-section are placed symmetrically on a vertical shaft. Transmission. Transmission lines carry electricity at high voltages over long distances from wind turbines and other energy generators to areas where that energy is needed. Transformers. Transformers receive AC, alternating current, electricity at one voltage and increase or decrease the voltage to deliver the electricity as needed. A wind power plant will use a step-up transformer to increase the voltage, thus reducing the required current, which decreases the power losses that happen when transmitting large amounts of current over long distances with transmission lines. When electricity reaches a community, transformers reduce the voltage to make it safe and usable by buildings and homes in that community. Substation. A substation links the transmission system to the distribution system that delivers electricity to the community. Within the substation, transformers convert electricity from high voltages to lower voltages, which can then be delivered safely to electricity consumers. Wind turbine tower. Made from tubular steel, the tower supports the structure of the turbine. Towers usually come in 3 sections and are assembled on site. Because wind speed increases with height, taller towers enable turbines to capture more energy and generate more electricity. Vanes at elevations of 30 meters, roughly 100 feet, or higher are also less turbulent. Wind direction determines the design of the turbine. Upwind turbines like the one shown here face into the wind, while downwind turbines face away. Most utility-scale land-based wind turbines are upwind turbines. Wind vane. The wind vane measures wind direction and communicates with the yaw drive to orient the turbine properly with respect to the wind. Anemometer. The anemometer measures wind speed and transmits wind speed data to the controller. Blades. Most turbines have 3 blades, which are made mostly of fiberglass. Turbine blades vary in size, but a typical modern land-based wind turbine has blades of over 170 feet, 52 meters. The largest turbine is GE's Haliade-X offshore wind turbine, with blades 351 feet long, 107 meters, about the same length as a football field. When wind flows across the blade, the air pressure on one side of the blade decreases. The difference in air pressure across the two sides of the blade creates both lift and drag. The force of the lift is stronger than the drag, and this causes the rotor to spin. Land-based gearbox turbine. The drivetrain on a turbine with a gearbox is comprised of the rotor, main bearing, main shaft, gearbox, and generator. The drivetrain converts the low-speed, high-torque rotation of the turbine's rotor, blades, and hub assembly into electrical energy. Nacelle. The nacelle sits atop the tower and contains the gearbox, low and high-speed shafts, generator, and brake. Some nacelles are larger than a house, and for a 1.5 megawatt geared turbine, can weigh more than 4.5 tons. Yaw system. The yaw drive rotates the nacelle on upwind turbines to keep them facing the wind when wind direction changes. The yaw motors power the yaw drive to make this happen. Downwind turbines don't require a yaw drive because the wind manually blows the rotor away from it. Pitch system. The pitch system adjusts the angle of the wind turbine's blades with respect to the wind, controlling the rotor speed. By adjusting the angle of a turbine's blades, the pitch system controls how much energy the blades can extract. The pitch system can also feather the blades, adjusting their angle so they do not produce force that would cause the rotor to spin. Hub, part of the turbine's drivetrain. Turbine blades fit into the hub that is connected to the turbine's main shaft. Gearbox. The drivetrain is comprised of the rotor, main bearing, main shaft, gearbox, and generator. The drivetrain converts the low-speed, high-torque rotation of the turbine's rotor, blades and hub assembly into electrical energy. Rotor. The blades and hub together form the turbine's rotor. Low-speed shaft, part of the turbine's drivetrain. The low-speed shaft is connected to the rotor and spins between 8 to 20 rotations per minute. Main shaft bearing, part of the turbine's drivetrain. The main bearing supports the rotating low-speed shaft and reduces friction between moving parts so that the forces from the rotor don't damage the shaft. Generator. The generator is driven by the high-speed shaft. Copper windings turn through a magnetic field in the generator to produce electricity. Some generators are driven by gearboxes, shown here, and others are direct drives where the rotor attaches directly to the generator. Controller. The controller allows the machine to start at wind speeds of about 7 to 11 miles per hour, mph, and shuts off the machine when wind speeds exceed 55 to 65 mph. The controller turns off the turbine at higher wind speeds to avoid damage to different parts of the turbine. Think of the controller as the nervous system of the turbine. Brake. Turbine brakes are not like brakes in a car. A turbine brake keeps the rotor from turning after it's been shut down by the pitch system. Once the turbine blades are stopped by the controller, the brake keeps the turbine blades from moving, which is necessary for maintenance.